I will introduce our paper, Nodens enabling results-efficient and fast queues recovery of dynamic microservice applications in data centers. I will introduce our work from these aspects. First, let me introduce the introduction and background. Current user-facing applications are shifting from the monolithic architecture to the microservice architecture, where a complex application is decomposed into multiple microservice stages, and different microservice stages communicate with each other through the network. Compared to the monolithic application, microservice-based applications can be easily distributed, deployed into data center clusters, and each microservice can be fine-grained results management to improve the results efficiency. The code dependencies among microservices can be donated by a DAG. Each node represents a microservice, and each edge represents a code dependency. The whole dependency graph is more like a tree, while less microservices have multiple integrates. There is typically an entering microservice, which is a front-end web service to receive origin queries. A production microservice application often has multiple call graphs, as users have different user patterns. A user query may only go through part of the microservices in the dependency graph. For example, depending on the user's selected recommendation method, the call graph of different queries may be different. Therefore, microservice applications have complex dependency structure and various call graph of user queries. Next, I will introduce the motivation of this paper. We analyze the production-level microservice trees that contains the microservice call dependencies across more than 3,000 applications. This figure shows the load variation of the microservices in the top 20 microservice applications. The load variation is defined to be the load changes in Jiuchen samples. We can observe the variation is from 10% to 40% of 70% of the samples. In the worst case, the load may increase by 2.3 times. We also found some of the top 20 applications have many types of call graphs. This figure shows the call graph proportion variation over time of the top 5 call graphs in the top 1 application. A call graph proportion variation is defined to be the proportion change in Jiuchen samples. We can observe the call graph proportions change dynamically. Therefore, microservice applications show obvious dynamic load and call graph characteristics. As current benchmarks do not support the dynamic call graphs, we built 3 benchmarks by integrating the call graph patterns of the trees and the actual microservice in the popular benchmark suite. Current microservice management work can be classified into proactive and reactive methods. Proactive methods predict the performance or load size for microservices based on the historical data. Most of them do not consider the call graph dynamics. Other work focuses on diurnal load and the call graph changes, but hard to handle the unpredictable dynamic cases that commonly exist. Reactive methods periodically monitor the latencies of microservices and adjust the results allocation based on the state. Some state-of-the-art work use ML-based methods to adjust different microservices individually. So we use the ADIS as a representative reactive method to investigate its queue's recovery time under microservice dynamics. ADIS use spatial optimization to turn results allocation. The queue's recovery time is the time needed to reduce the 99th percentile latency to be below a fixed latency target after microservice dynamics happen. We use the 3 benchmarks with 18 load and call graph dynamic cases. The queue's recovery time is ranged from 24.6 to 84.4 seconds. Therefore, both the 2 types of dynamics result in long queue's recovery time. There are 3 aspects leading to the long queue's recovery. First is the long monitoring interval. Current methods monitor the real-time latencies of the microservices and adjust the results based on these latencies. This system often needs seconds or even tenths of seconds to be the monitoring interval. The example shows the latency change after we increase the application load to 1.5 times. We can observe the monitor latency needs about 3.3 seconds to increase to a stable state. This is because the latencies of the newly arrived queries can only be reported after they complete, which takes some time. Therefore, the latency monitoring interval needs to be long enough, which enlarges the queue's recovery time under the microservice dynamics. The second is that the monitor real-time load of a microservice may not be its actual to be precise load. As an example, the load of microservice 3 may be blocked by microservice 0 if microservice 0 does not have enough computation resources. Same situation applies to microservice 8, 9, and 3. The effect is referred to be the execution blocking effect. This figure shows the latencies of microservices under a dynamic case when we allocated their super microservices enough resources, normalized to insufficient resource allocation. The latencies of many microservices increase when their super microservice get enough resources. This is because this microservice may get the real to be precise load when the blocking effect is elevated. Therefore, current method based on monitor load may not allocate enough resources at the beginning and require to adjust the resource allocation for multiple times, and thus need long queues recovery time. The third problem is the Quan queries can result in the long queues recovery time. As an example, figure A shows the 99th percentile latency with Addis under a dynamic case. We can observe although the just enough resources are allocated to the microservices, the 99th percentile latency gradually drops for about 8 seconds instead of backing to the normal immediately. This is because the Quan query at microservices need extra time to be trained under just enough resources. We future try to allocate excessive resources for microservices. We can observe that the larger the excessive resource allocation ratio, the shorter the training time. Therefore, it can reduce the Quan query training time through excessive resource allocation so that it can reduce the overall queue's recovery time. To address the above problems, we propose a runtime system called Nodens to enable fast queues recovery under microservice dynamics while maintaining the resource efficiency. Nodens mainly comprises of 3 models. The traffic-based load monitor obtains the monitor load of each microservice based on the monitor network traffic of each microservice. The blocking-aware load updater consists of 2 parts, execution blocking graph and actual load updating. For each microservice application, we first construct the execution blocking graph to capture all the possible blocking relationships among different microservices. Then the actual load updating mechanism updates the real to be precise load of microservices based on the execution blocking graph. At last, the resource-efficient query trainer allocates just enough excessive resources for each microservice to train the Quan queries in a quick time while maintaining the resource efficiency. In the load monitor, we first obtain the upper network bandwidth usage of each microservice. For this example, microservice 6 upper network bandwidth usage is the data communication amount per second from microservice 0, 2, and 3. For the tree-like and graph-like dependency graph, we utilize different methods to obtain the upper network traffic of microservices. Then we use the linear models to predict the monitor loads of microservices based on the network traffic, and finally input the results to the load updater. The relationship between the load side and CPU core demand of microservice also have linear relationship. And to explore the execution blocking effect, we conduct an experiment under a dynamic case with load and call graph dynamics. This figure shows the normalized monitor load to the actual load of the microservices. Since the load is increased to 1.5 times, the monitor loads of most microservices are about 1/1.5. Due to call graph change, some microservice monitor loads are about 1/3. So the execution blocking effect can be caused by the call dependencies among microservices. Moreover, microservice 5's monitor load is about half of its actual load, and microservice 4 and 5 are called in a fixed order. The subtree of microservice 4 can block the load to microservice 5. Therefore, the execution blocking effect can be caused by the call order among microservices. For a simple example, suppose queries go through first login, second authentication, and the third reservation. Suppose microservice 3's load increased to 1,500, but it only has just enough resources to handle 1,000 load. At that point, the loads to its downstream microservices are blocked at 1,000. The execution blocking graph construction process is shown in this figure. First, for the microservice that has multiple integrates, we transfer the subtree with it to multiple identical replicas. We then construct the execution blocking relationship for each substructure. If microservice X and Y have no fixed call order from their common superior microservice, the execution blocking relationship is equal to the call dependencies. If X is called before Y by their common superior microservice, the execution blocking microservice of Y are the ends of the subtree with the root of X. For a simple example, suppose X is authentication and Y is the reservation and Z is the login. As X is called before Y by Z, the resource efficiency of X can block Y. If I and Y are called by Z asynchronously, X cannot block Y. In the actual load updating, since microservice may block the load of their downstream microservices, we first define the blocking rate of each microservice. The major process of the load updating follows the breadth-first search process of the execution blocking graph. Starting from the entering microservice, we first calculate the blocking rate of the microservice at the front of the BSI screen. Then we update the actual load passing to its downstream microservices using this blocking rate. After a microservice or entry edge have been updated, this microservice is pushed into the BFS screen. After the whole BFS process, all microservices' actual loads have been updated. Please refer to our paper for more design details about this model. For the current joiner, we first set the queue's recovery time target for the microservice application. For example, the queue's recovery time is within 3 seconds. Therefore, the excessive resource allocation of microservice can be described as minimizing the excessive resource allocation while ensuring the recovery time target. The current joiner will first calculate the overload for each microservice. It then calculates the total query and total load for each microservice to precise in remaining time. At last, the current joiner decides just enough excessive resources for each microservice based on the obtained total load. Please also refer to our paper for more design details for this model. Next, I will introduce the evaluation of Nodens. We use an 8-node server with 3 benchmarks. The evaluation is conducted under 18 dynamic cases with load and call graph dynamics. We compare Nodens with 2 state-of-the-art baselines. We optimize their ML-based resource adjustment to directly allocate the optimal resources for each microservice after monitoring the load change. We also use the same amount of excessive resources to Nodens query joiner for baseline to speed up the training process of the baselines. In all test cases, microservices are initially allocated just enough resources when the load is one time, and different call graph proportions are identical. Then we change the load and the call graph proportions of the entire benchmark. The results show that Nodens can eliminate queue's violation in given queue's recovery time target in all dynamic cases. Nodens can reduce the queue's recovery time by 12.1 times and 10.2 times than the baseline, respectively. Firm also has shorter queue's recovery time than Alice as it directly adjusts the critical microservices to recover the queues. This result proves that Nodens has shorter queue's recovery time when dealing with microservice dynamics. We further evaluate Nodens resource usage during the queue's recovery period. We use the longest Alice queue's recovery time to calculate the total resource usage for fair comparison. This figure shows the corresponding total resource usage of all the test cases. Nodens use 1.5% and 6.1% more resources on average than the baselines, respectively. Firm also use more resources than Alice, as Alice spent extra time to actively recycle the over-provisioned resources. Therefore, nodes use a small amount of more resources to enable fast queues recovery, which also maintains the resource efficiency. In this experiment, we compare nodes with nodes WOU to explore the effectiveness of nodes load updater. Nodes WOU is a variant of nodes that disables the load updater. As the orange bar shown in this figure, nodes WOU only recovers queues within recovery target in 2 cases and requires 2.6 times time to recover the queues compared to nodes. This figure shows the resource allocation process in one test case. Nodes allocates enough resources to the microservices at an early time, while nodes WOU gradually increase the resources after each monitoring interval. This is because the execution blocking effect makes nodes WOU only obtain the actual load of microservices layer by layer. Therefore, the blocking-aware load updater can avoid the execution blocking effect by updating the actual load in advance. We further compare nodes with nodes WOD to explore the effectiveness of nodes query joiner. Nodes WOD is a variant of nodes that disables the query joiner. As the green bar shown in this figure, nodes WOD fails to recover the queues within the recovery target in all cases and requires 1.6 times time compared to nodes. This is because the current query cannot be joined up quickly without the current joiner. This figure shows the excessive resource allocation in one test case with nodes. We can observe nodes can allocate just enough excessive resources to microservices based on their affection degree by execution blocking. Therefore, nodes query joiner enables to join the queries quickly while maintaining the high resource efficiency. At last, I will conclude our work. There are 4 main goals in our work. First, to monitor the load change of microservices quickly. We monitor the upper network traffic for microservices and obtain the monitor load of them based on the traffic data. Second, to capture all blocking relationship in a microservice application, we construct the execution blocking graph based on the call dependencies and the call orders among microservices. Third, to update the actual load of microservice in advance, we calculate the blocking rate of microservices and update their actual load based on the execution blocking graph. And at last, to join the current queries quickly, we allocate the microservice just enough excessive resource to enable fast and result-efficient query joining. In summary, under microservice dynamics, above technicals enable nodes to realize fast queues recovery while maintaining high resource efficiency. All right, that's all for my presentation. Thank you.